law of kinetic friction. Sorry, I have written here the wrong thing. Oh yeah, it's correct. Sliding friction, not static. So this is related to sliding friction. So this law is related to sliding friction. So this law talks about factors that influence the opposing force on objects that are already in motion. So we have something in motion, right? But that does not mean the frictional force will disappear. Okay, this is not visible. Let me change to rubber. So I'm trying to move steel over a rubber surface. Right? So here the object has started to move. Has the friction disappeared? Yes or no? Right? The friction has not disappeared. So that being the case, we have laws related to friction that comes up during motion, sliding basically. Okay, let's have a look. Normal reaction. So by default, friction is related to your normal reaction. The kinetic friction is directly proportional to the normal reaction between the two surfaces. This is expressed as f of k is equal to mu k into n, where mu k is coefficient of kinetic friction. Again, here too, it's independent of area, right? Like your static friction. The same thing over here as well. Dependence on nature of the surface, that is taken care by your coefficient of kinetic friction, mu k. And independence of velocity, this is the new one. The kinetic friction is generally considered independent of relative velocity between the surfaces, provided the velocity is not extremely high. So then things are different. So over here, once I start applying, see, after a certain point, what happens? Can you see that? Whatever I do, if I apply force, what is happening? Look at the graph. So for this, I need to explain. I mean, you guys should be able to. Actually, let me take this entire thing. You guys should be able to look at this and be able to explain. See, what we looked at was I have increased the forces over here. So this is your applied force along the x-axis. Okay, so this is your applied force, right? As you can see, I'm increasing the applied force over here. So this is a point wherein it's increased. This is a point wherein it's increased. But you can see the frictional force, it has remained the same, right? So you can see, I don't know how, oh yeah, I can zoom in. So this blue is your frictional force. This is your applied force. Applied force is, as you can see, it's increasing, but the frictional force remains constant. So for certain, again, certain limited value, the frictional force will be constant. After it starts moving, it will remain constant. So it's independent of velocity. Again, let me go from static. So in static, we saw the direction. Oh yeah, here too the direction will remain the same. It's always tangential. There too it will be tangential. Depend on the nature of surface. In kinetic too, it depends on the nature of the surface. Same thing, there's no difference. Independent of area, there too it's independent of area. Directly proportional to normal reaction. There too it's directly proportional to normal reaction. Only thing is, the extra bit over here is, it's independent of velocity. Again, here too it's directly, it's quite simple. It's independent of velocity. And finally, we have the mathematical expression. Fk is equal to mu k times of n. So once the object starts moving, the factor, the new set of factors is combined to form something called as mu k. Mu k is your coefficient of kinetic friction. So all of this we will understand better with numericals and you get familiar. But yeah, pretty much honestly, everything is happening over here. All the things we need to know about static and kinetic friction, you have to learn from this particular graph. You should be able to understand this graph actually. Okay, so yeah, now it's time for you guys to copy this off. For independence of velocity, you guys should be drawing this. So you need to make yourself, explain it to yourself that same frictional force for different applied force.